So for the first learning module of Chapter 7, I'm going to give you a big introduction to the big idea of this chapter, which is about internal forces. So you've probably been driving around and you've looked at some kind of support structure, maybe like the column that's shown supporting the billboard here in the figure on the right. And one of the things that you've noticed is that whoever has chosen to design the support structure, they've not made the cross-section uniform. So the majority of your support structures, if you think about them in everyday life, they typically have a uniform cross-section, whether it's like in a framed out building construction around you, a 2x4, or maybe an I-beam in some type of commercial construction. The general rule of thumb is to make things have a uniform cross-section. So if they don't, there must be some kind of motivation behind that. And one of the things you might think is, well, I need that support structure to be stronger there. Well, what are you really trying to say by that? You're saying that there must be something going on internally. There must be some kind of internal stresses that just are greater at the bottom of that support than the top. So that's kind of what we're going to learn about in this chapter, is how to do the analysis in order to determine at a given location along our supporting member how the internal forces look. And we kind of need to talk about like how we actually model them. What is the general modeling approach that we use in order to describe those internal forces? So that's kind of what we're doing here. And it kind of relates back to the ideal that we looked at briefly in Chapter 6 when we talked about trusses and frames. Because there we said when we were doing method of joints or method of sections, what we were trying to determine is how much tension or compression each of those members were under. That way we could design the individual members appropriately. So in terms of developing a model for the internal forces inside of a load-bearing structure, we're going to just, and if you want to, I'm going to take just a few more minutes. I know we're all busy this week, but let's just actually think about it. Think if I was going to try to break this pen, all the different ways that I could break it. One way is I could just bend it, right? And everyone would know how it would just crack, right? So we've seen failures that are basically resulting from someone trying to bend something too much. So when I'm pushing on this, if the pen is normal, and then I push on it and it's still normal, there must be something going on internally that's kind of counterbalancing that tendency that I'm inducing on it to bend. And what that's known is as a bending moment, right? So it's not surprising that internally within a member in equilibrium, in general, I could have a bending moment that each part of the structure is exerting on the other in order to stop it from bending. In addition, it would be very, very hard to do. I'm not strong enough to do it. But I can just pull this apart at both sides and it can eventually just pull into two sections, right? And in that case, when I have no load on it and when I'm pulling as hard as I can, there must be some internal forces going on along the cross section that are tending to one section pulling on the other section to keep it together. So like if you think about splitting that pen, and here's the right side of the pen, here's the left side. The left side must be pulling it back towards it. And in a similar fashion, the right side must be pulling it back towards it in order to keep it together when it's subjected to that force. And I could have not pulled it together. I could have pushed it together, right? I could have put it in compression. So in general, there must be some normal force internal to a member that tends to oppose those kind of stresses that I'm putting on it in that in external loading condition. In addition, I could apply a sort of shear force where I take one part of my pen and I pull it downward to the right, and I take the other part and I push it directly upwards. So it's kind of a little bit different than a bend. And that hopefully will convince you that in addition to the normal force, which when I segment a surface is perpendicular to the surface, there must be a internal force which is parallel, which we'll call the shear force. So get familiar with this. This is just a model to describe for any loading condition what the internal forces of a member must look like. One force perpendicular to the surface, denoted by N, which is the normal force. One parallel to the surface, denoted by V, which is the shear force, along with a bending moment. So in terms of how you analyze these types of problems, it's not surprising to you that in general, you're just going to be given a body, you're going to be given a visual description of the reactions that tend to keep the entire structure in equilibrium, and you're going to ask to find the internal forces at one point. So usually, before you can find those internal forces, even though what you'll see is that these ultimately just boil down to equilibrium of rigid body problems, if you try to, like, say, for example, here, if someone wanted to find the internal forces at this point in the beam, and they just said, okay, well, I know if this beam is in equilibrium, then both the left and the right side must be in equilibrium. So I'm going to draw a segmentation, and I'm going to look at the two free body diagrams that I get. Well, remember that those internal model of the forces, they have three unknowns right away. So if you segment this anywhere, Since any place you segment it, you're also going to have one of the two unknown reactions, you're going to get a statically indeterminate situation. So usually the way that this works best is if you analyze the entire beam as an unsegmented rigid body first, find the external reactions that are tending to keep it in equilibrium, and then once you have those, actually do the internal analysis. Now, once you've worked a bunch of these problems, one thing you find is you generally don't have to find both of the two reactions if you're only interested in the internal forces, because you always have that freedom when you make your segmentation of which side you actually solve for. What I mean by that is, say like I did some analysis and I just found dy, which I could do by just summing all moments about point A from an entire rigid body analysis. If I just had that and I was interested in finding for the internal forces at some point, I could just work with the right side of my free body diagram and I would have all the forces that I need. So I'd have a statically determinate situation. So let's look at an actual example. Here we have a beam that's under a relatively bizarre type of loading condition. We have a roller at A, so it's only going to be able to oppose normal forces. So we'll have an unknown vertical reaction at AY. And at B, we have a pin, so we'll have an unknown vertical and horizontal reaction. We have this distributed load from the beam's end to point A, and we want to find what's going on here. What are the internal forces at C? So if you kind of think when you're going to segment this into left part and right part, doesn't the right part just look easier to work with? Because you'll have those unknown forces that you're introducing when you make the segmentation, along with just the reactions at B, which based upon your exam performance, I know everyone knows how to do that pretty well. So let's first just try to find what this reaction at B is. So if I draw a free body diagram of the entire beam, notice I've modeled the pin connection by an unknown vertical and horizontal reaction, and I've modeled the roller connection by an unknown vertical reaction. And the book's kind of weird here in that they're taking liberty to, I mean, it is kind of intuitive, but one of the things I hate about this book, and it's hard to pick one because I don't like a lot of it, is how they are inconsistent against themselves. So one of the ways you can get in the most problems when you're doing problems in mechanics is to violate your own assumptions. If you're a double E, the same thing happens when you analyze circuits. If you don't always assume circuits go in one, currents go in one direction. The rules of thumb exist for a reason. So anyways, enough, I'll digress here. But if we add this free body diagram, the first thing hopefully everyone notices is that under this loading condition, the horizontal reaction at B is 0. It's nice that this pin can oppose translational motion in the horizontal direction, but if it's not loaded that way, that reaction will always be 0. However, I can determine the vertical component of the reaction at B by just summing all moments about point A. And hopefully everyone's getting the hang of this now, right? The issue is if I sum all forces in the vertical direction, I have two unknowns, only one equation. So usually in situations where we have two unknown vertical forces, we sum moments around the one we don't want. So if we want BY, we'll sum moments about AY. What do we find when we sum moments about AY? That 18 kip force is going to introduce a counterclockwise rotation. The perpendicular distance from A to the 18 kip force is 3 feet. So it'll just be 18 times 3, and that'll be positive. That's where that's coming from. The reaction BY, if you notice, based upon the geometry that they've drawn, and which is correct, right? It's going to counterbalance the tendency of the 18 kip force to rotate in the counterclockwise direction. It's going to rotate back in the clockwise direction. So that's why for this direction, which is shown, that's going to be minus unknown BY. That's 9 feet separated from point A. You can get this math pretty easy if you just look at it. Since BY is 3 more feet away, right? Remember, this is the old concept of just a torque or a lever. Think about it as having a wrench that's 3 times as long. If you got 3 times the perpendicular distance, you only need 1/3 of the force. So you can just divide 18 by 3 and you get 6, or you can solve that equation if you like. So now we have enough information such that when we cut this beam at C, we can have a statically determinate situation. We know that the reaction at B is only the 6 kip force, which is directed downward. We know that from point C to B, that's 4.5 feet. We draw in our unknown shear, our unknown normal, and our unknown bending. The book, again, is doing it a little bit weird from a sign convention. Usually you always draw and I want to be clear, there is no right answer here because they don't have the left portion of the free body diagram drawn. If they had the left portion of the free body diagram drawn, you could critique them and say that each of these better be equal and opposite the other side. However, if you're only drawing one free body diagram, assume them whatever way you want. And clearly it's kind of weird that they've assumed VC the way that they've shown. given that we know VC will have to be vertical. But the math will all work itself out. So working the math out, we notice that under this, if this were just a rigid body, it happens it's a part of a beam. But if it were just a whole beam, if there are no horizontal forces, then NC must be 0, which is saying that there is no tendency, there's no internal compression or tension at that point, which isn't surprising because the entire beam is not subjected to any forces that would induce tension or compression. If we compute what MC is, that's just going to say that basically the tendency of this beam to bend at point C. So let's go down here. And I want to make one thing clear. Why doesn't the shear force, VC, contribute to the moment about point C? Well, remember, it's passing, its line of action passes directly through C, even though you're drawing it with a little bit of an offset. So it won't contribute to rotation here. What this bending moment is describing is basically the tendency of this reaction at B to bend the beam at point C. Well, how would I compute what that is? Well, if I compute all moments about point C, notice that the 6 kip force is going to induce a clockwise rotation, so it's negative by convention. Magnitude of the force is 6 kips. Perpendicular distance is 4.5 feet. That's offset by, because of the direction they've shown MC in the clockwise direction, that will be negative. So little error on the book here. They should have this as hopefully everyone's watching the video and not just reading the sides. I'm actually going to erase this beforehand because that's an error on their part. What the sign convention that they're showing is counterclockwise positive, which is usually one we show, which is why both of these are negative. Just do the math and you find that relative to the direction they've assumed, MC actually turns out to be negative 27 kip feet. Usually you don't show signs like this. You'll see when I actually write the example by hand. You just write the magnitude and you show the direction. So the preferred way to write this would be 27 kip foot in the counterclockwise direction. Just put a counterclockwise after it. Same thing here. VC, or the shear force, is just 6 kip upwards. So hopefully that makes sense to everyone. Key point that I want everyone to take away is there is nothing new here. There's zero new here. The only real new thing, after I say there's nothing, I'll say there's something new, is you need to know that in general, in a beam, when you segment it, there are 3 unknown internal forces: the shear force, which is parallel to the surface, the normal force, which is perpendicular, and the bending moment. And in analyzing these problems, it's really just a matter of taking a segment of the beam and finding which side is statically determinate, which will usually require you to solve for the entire beam in equilibrium in order to solve for the reactions initially. And in the next video, I'm going to set up the problem that will be useful for your final exam.